Recently, uranium has become a major topic in the news and in online discussions. The term enriched uranium has become one of the most searched scientific expressions on the internet. You have probably heard it before, but do you know what it actually means? Enriched uranium is a material that carries a fascinating paradox within its atoms: the power to sustain modern civilization and the potential to destroy it. Behind this technical name lies a story of brilliant minds, extreme engineering challenges, and geopolitical decisions that shaped the 20th century. But what makes this substance so unique, and why does mastery of its technology divide nations and scientists? The beginning of the story. Everything starts with uranium in its natural state. Discovered in 1789 by the German chemist Martin Heinrich Klaproth, uranium soon revealed itself to be one of nature's most intriguing substances. It is about 70% denser than lead, meaning a simple cube measuring 10 centimeters on each side would weigh roughly 19 kilograms. Chemically, it occupies position 92 on the periodic table and is naturally radioactive. But why was this radioactivity revolutionary? The answer emerged in 1935, when physicist Arthur Jeffrey Dempster demonstrated that natural uranium is actually a mixture of two isotopes. Uranium-238, U-238 about 99.3% of natural uranium. Uranium-235, U-235 only about 0.7%. The difference is subtle but crucial. U-238 contains 146 neutrons, while U-235 contains 143. This tiny variation dramatically changes how each isotope behaves when struck by neutrons. The discovery of nuclear fission. In 1938, chemists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and detected atoms of barium, a much lighter element. Physicist Lise Meitner correctly interpreted the result as nuclear fission. The uranium nucleus had split in two, releasing enormous amounts of energy. In 1939, physicist Niels Bohr confirmed that only U-235 readily undergoes fission when struck by slow neutrons. The fission process releases additional neutrons, creating a chain reaction. U-238, the dominant isotope, generally absorbs neutrons without significant fission. So, what is enriched uranium? Enriched uranium is simply uranium in which the concentration of U-235 has been increased. The challenge is that U-235 and U-238 are chemically almost identical. Separating them requires exploiting their tiny difference in mass. How uranium is enriched. The process begins by converting uranium ore into uranium hexafluoride, UF6, a corrosive compound that can exist as a gas. This allows uranium to be manipulated in gaseous form. In the most common modern method, gas centrifugation, cylinders made of special steel or titanium spin in a vacuum at speeds of up to 70,000 revolutions per minute. Inside them, the uranium hexafluoride gas experiences forces up to 100,000 times Earth's gravity. Here, physics performs its magic. Molecules containing U-238 are slightly heavier and move toward the outer wall. Molecules containing U-235 remain closer to the center. The slightly enriched gas is extracted and sent to another centrifuge. Thousands of centrifuges are connected in cascades, repeating the process hundreds of times until the concentration of U-235 rises from 0.7% to as much as 95%. Why enrichment is expensive? Producing fuel for nuclear reactors, which typically contains about 5% U-235, requires enormous amounts of energy and sophisticated infrastructure. Producing weapons-grade uranium, which generally contains 90% or more U-235, is far more demanding and requires many additional stages of enrichment. What different enrichment levels are used for? U-235 concentration. Main use: 0.7%. Natural uranium. Heavy water reactors such as Canadian CANDU reactors. 3 to 5%. Fuel for most commercial nuclear power plants. Above 20%. Highly enriched uranium used in some research and naval reactors. 85–90% plus. Weapons-grade uranium suitable for nuclear weapons. Peaceful uses. Despite its dangers, enriched uranium has important peaceful applications. Naval reactors in some submarines use highly enriched uranium because of its extraordinary energy density. A tiny amount of uranium can provide the energy equivalent of tons of diesel fuel. Research reactors also produce medical isotopes such as technetium-99m, which is used in a large majority of nuclear medicine imaging procedures worldwide. The global political challenge. Because uranium enrichment can produce both reactor fuel and nuclear weapons material, it is one of the most sensitive technologies in the world. The Treaty on the Non-Proliferation of Nuclear Weapons, NPT, signed in 1968, seeks to limit the spread of nuclear weapons while allowing peaceful nuclear energy under international inspection by the International Atomic Energy Agency. Disputes over programs such as the Iranian nuclear program demonstrate how fragile this balance can be. The ethical question. Enriched uranium is neither inherently good nor evil. It is a technological tool that amplifies a quantum phenomenon to a human scale. In the right hands, it can generate electricity for millions of people and produce life-saving medical isotopes. In the wrong hands, it can become one of the most destructive materials ever created. The central challenge for humanity is how to balance energy, progress, security, and responsibility.